So, oxidation numbers. You are going to use oxidation numbers for the rest of chemistry. And what we're talking about with oxidation numbers is not, when you think of oxidation, you think of fire. And that's because fire is the process of something being oxidized. But oxidation states, it's not is the thing on fire or not. It's have I lost electrons and am I going to get them back? That's what we're talking about with oxidation states. So when you look at an atom's oxidation state, you're asking the question, how many electrons has it lost? Or you could ask, how many electrons does it need to return to a natural state or a neutral state? So if you pick fluorine, for example, fluorine likes to get electrons. It really, really badly wants one more electron to make itself happy because it wants a valence energy shell to be full, right? So when fluorine gets one more electron, we can ask the question, how many more electrons does that fluorine atom need to go back to being neutral? Well, it needs to lose the one it got to go back to being neutral. So it needs -1 electrons to go back to its natural state. So its oxidation number is -1. A magnesium ion, magnesium wants to give away the 2 electrons that it has, which is why it becomes a +2 ion. So when magnesium gives those electrons away, we ask the question, how many more electrons does it need to return to the natural state? It needs 2, because it gave 2 away. So its oxidation number is 2. The oxidation number is almost always the same thing as the atom's ionic charge. For things that become an ion, like fluorine and like magnesium, the 2 examples I just gave you, you could ask yourself, what's the ionic charge of the atom at the moment? That is also its oxidation number. Okay, so it's easy to get the number most of the time. The transition elements that are in the middle of the table, and we haven't played with them very much yet, those guys are happy with a different number. They don't seek the octet rule. They, remember, they're communists, right? So they're okay with not having enough because maybe their neighbor does, or they're okay having a surplus, and they all share electrons. So oxidation numbers for transition metals are a little bit of a different thing. And when we look at what's the oxidation number of a transition metal, or some of those other ones that can form larger than an octet that we were messing with, then you have to get a little bit more careful with how you calculate the oxidation number. But for the majority of the atoms that you're going to be playing with, you can just look at it and say, what kind of ion does this form? What electrons has it gained or lost in this particular situation to make this bond? And that ionic charge is the same thing as the oxidation number. So if it has gained electrons, it needs to lose those electrons to go back to a natural state. So it will have a negative oxidation number. If it has given away electrons, it needs to gain those electrons back to get back to a natural state. So we'll have a positive oxidation number. So the oxidation number and the charge are the same number the majority of the time. Okay? And you may ask yourself, why do I need to know this? Because we're going to be tracking electrons in chemical reactions. And you need to be able to look at a chemical reaction and say, this electron has gone, or not this electron, this atom has gone from an oxidation state of something to an oxidation state of something else. And where did those electrons go? And you need to be able to find the electrons somewhere in the equation, somewhere in the reaction. Watch the electron move in a chemical reaction. That's where we're going with this. So calculating an oxidation state makes it possible to follow electrons through the flow. Okay. The other quick thing we're going to look at is naming compounds. So take a moment and write that down. Okay, so naming compounds. 8B in your book is about naming compounds. And this is fairly convoluted, but once you understand it, you can switch between the name of a chemical and its compound formula, its structural formula, really easily. And so knowing how to name a compound and knowing how to understand what that name tells you the compound is important as we move forward in chemistry. There's lots of different kinds of compounds. The first one we're going to look at is a binary covalent. Binary means only two atoms. Okay? Not just two atoms, two kinds of atoms, two elements involved, right? And a covalent, these are all covalent bonds. If it's a binary covalent, then there's a set of rules for how you name this thing. Water is a binary covalent because there's only two kinds of elements, and carbon dioxide is a binary covalent because there's only two kinds of elements. So we could name either of those this way. The way we do it is we use Greek numerical prefixes: mono, di, tri, tetra, etc. Okay? So you're familiar with those. You've used those a lot in lots of things in your life. So we talk about how many of each thing there is. So water, we call it water, but pretend you don't know that that's called water. We would look at this and we would say that there's two hydrogens. Dihydro or dihydrogen. Okay, two hydrogens. Monoxide, one oxygen. We understand that underneath the O, there's a pretend one there, right? If there's not anything else written, there's one. So one oxygen, mon-ox, okay? One oxygen. And then "-ide", we put "-ide" at the end of the name. Anytime you see "-ide" at the end of a name, you know that it's a covalent bond. So water should be called, we didn't call it water, dihydrogen monoxide. Two hydrogens, one oxygen. Okay? Carbon dioxide we refer to in its proper name. Okay? If there is only one of the element, you say mono something, unless it's the first part of the name. For some reason, they don't ever say monocarbon dioxide. They only use mono if it's the second element. So carbon, and because it's not dicarbon or tricarbon or tetracarbon, then it's one of them. Carbon, di-ox, two oxygens, "-ide" at the end to tell you it's a binary covalent. Okay, so these are the rules for how to name something. Carbon tetrafluoride. What would the formula for that be? Carbon tetrafluoride. CF4. See? Not hard. Not hard, right? Beryllium triphosphate. Triphosphide. Beryllium triphosphide. BeP3. Yeah, good. So not hard to do this stuff. So we call it water, but its other name is dihydrogen monoxide, right? Okay. And carbon dioxide, carbon assumed to be one unless it's specified, di-oxygen, so there's two oxygens. That's how we do it. Similarly, ionic compounds have their own names too. Okay, very, very, very similar. Binary covalents, we always use the Greek prefixes. Binary ionics, we do not. So still binary, only two kinds of atom. Ionic though this time. So sodium and chlorine are not covalently bound to each other. They are ionically bound to each other. So we wouldn't call this sodium monochloride. If we used mono, then somebody reading it would say, oh, this is a covalent compound. We don't say mono. We don't use Greek prefixes, and that lets the person reading it know it's ionic. Okay? So sodium chloride, potassium iodide. That's all you have to do. Okay? So we name the metal first. Binary ionics is usually a metal and a non-metal. Not usually, it's always a metal and a non-metal. So we name the metal first, and we name the non-metal second. And just like in the covalents, we use "-ide", and "-ide" tells us that it's two things that have been joined together in a bond. If we use Greeks, then it's a covalent. If we don't use Greek prefixes, then it's an ion. Okay, so very simple. So far, not too hard. So again, Table salt, its other name is sodium chloride and potassium iodide. Okay, it's a little bit more polyatomic ions. So these are the covalently bound molecules. They are covalent, but they as a molecule have a charge. And we talked about these when we were drawing Lewis structures and drawing structural formulas. We talked about a covalent molecule that gains or loses electrons with something else in the universe. And this molecule has a charge. And that's a polyatomic ion. When these polyatomic ions get into a larger molecule, we name the larger molecule as if this were just an ion. But then the name of that part of the molecule helps us understand what's in that part of the molecule. So the polyatomic ion, its name is based on the central atom, whatever the not oxygen component is, and then how much oxygen there is. Now, there are polyatomic ions that are not based on oxygen, but they're the exception. The huge majority of the time, a polyatomic ion is some non-oxygen atom and oxygen. And so, and oftentimes that polyatomic ion, there could be several versions of that are different from each other based on how much oxygen they have. And so we have different ways of naming the polyatomic ion based on their oxygen content. So there's 4 ways to name a polyatomic ion. There's a name that means I have as much oxygen as I can have. There's a name that means I have a lot of oxygen. There's one that says I don't have so much oxygen. And there's one that says I have almost no oxygen. Okay? So there's 4 levels to the amount of oxygen that it can have. And this is where it's a little bit strange. So there's 2 suffixes and 2 prefixes. So if you kind of picture a line dividing, and I should have probably drawn a line on the slide. Draw a line between 8 and ite, right? 8 as a suffix means I have a lot of oxygen. Ite as a suffix means I don't have all that much oxygen. If there's only 2 kinds of a polyatomic ion, so like sulfate and sulfite, SO3, SO4, you would name the one that has more oxygen, sulfate, and the one that has less oxygen, sulfite. And that tells you that between the 2 kinds, the one that has more, SO4, is sulfate, and the one that has less, SO3, sulfite. So that's good. But what happens if you have options where there's 3 or 4 kinds of an ion, like there is for the chlorine one that I gave you as the example? Now you would leave the 8 and say, I've got even more than the 8. And that's per something 8. And the per going in front means, wow, so much oxygen you can't believe it. Or you have hypo, which can be a prefix that means I have even less than the ite. So for the chlorine-based polyatomic ions, there are 4. There's ClO4, ClO3, ClO2, and ClO. And so to set them apart, we use 8 for the 2 that have more oxygen, ClO4 and ClO3. Both end in 8 because they've got more. And ClO2 and ClO both end in ite because it's the lesser 2 options. And then to set the one that has the most and the one that has the least off, we use prefixes. So 8 stays there, and we add per. And now perchlorate means I've got the most oxygen, ClO4. And hypo gets added to chlorite to represent ClO. I have the least amount of oxygen. So this is going to come with practice, and this is going to come with seeing these words a bunch. When you first look at it, you're like, well, how do I know? Like, how do I know sulfate means SO4 And sulfite means SO3 because there's nothing there that tells me 4 and 3, right? You just gotta have to get used to using the words, and you'll recognize there's no such thing as SO2. There's no such thing as SO5. And so I know there's an SO4 and there's an SO3. Which one is which? The 8 has more. Sulfate is SO4, sulfite is SO3. So this just comes with practice because the word does not tell you 1, 2, 3, or 4 oxygens. It doesn't. It just tells you more or less, or wow, lots and hardly any. That's all the words mean. So this is just going to come again with seeing these words a whole lot of times. You cannot draw the structure for chlorite just based on chlorite. The only thing you know about chlorite is that it has a chlorine and it has less oxygen than something else. So that's all that that tells you. So you're going to have to become familiar with this. So this just takes practice. But once you do know perchlorate is ClO4, then if you see something and you see, I'm just going to make one up, magnesium perchlorate, then you would be able to say, okay, magnesium perchlorate, that's a diatomic, I'm sorry, that's a binary molecule. The metal is magnesium. And the non-metal, instead of being like magnesium chloride, which would mean MgCl, it's magnesium perchlorate, MgClO4. Okay? So these things represent almost always the negative ion to a binary ionic molecule. And you're just going to have to practice and play with them and make them your friends. That's all there is to it. Okay? Okay, I think I've got one more type of naming here. Where's my mouse? Okay, so multiple oxidation states. First part of this chapter was oxidation states. We just briefly recapped it where it's essentially the charge of an ion unless it's something in the middle of the table of transition metals. When you're talking about a transition metal, you don't know what oxidation state it is because it's not something like magnesium or fluoride or whatever that just always goes to that particular charge. So we have to tell the person reading our name what oxidation state that atom took in this molecule. So first you have to find that out. And then once you found that out, it would go into the name as a Roman numeral. So in this particular molecule, FeO, oxygen always has a -2 oxidation state if it's in a bond. So in order to be balanced, the iron here must be currently a +2 oxidation state. So then we would tell the person that in this particular molecule, iron has adopted a +2 oxidation state. And so we would say iron 2 oxide. And that lets the person know that this is FeO. Because there are options where iron takes on a +3 oxidation state. And in that case, if iron were 3 and oxygen is always 2, well, now you've got to have a different formula. You'd have to have Fe2O3 to make it balanced. So we've got to tell the reader, hey, this is iron, and because iron can do different things and iron is strange, in this particular molecule, iron is a +2 oxidation state. And it's sitting there hanging out with oxygen. So it's iron 2 oxide. Okay? And here's another example, tin oxide. Tin can be lots of different charges. And so in this particular one, SnO2, there's 2 oxygens. Oxygen always has a -2 oxidation state. So if there's 2 of them, well, I've got a total of 4 electrons here that are making this part of the ion of the molecule what it is. It has gained 2 electrons each, and so it's gained 4 electrons. That must mean that tin has given those away. So tin must be a +4 to balance the oxygen. So SnO2, looking at the molecule, tin has a +4 oxidation state. So I tell them that in the Roman numerals. This is tin 4 oxide. Because tin can go 3 and tin can go 2. Tin can do all kinds of things. So, but in this particular molecule, it has an oxidation state of 4. So we tell them that, tin 4 oxide. Okay? Questions on that? You understand what that Roman numeral means? It means that's the oxidation state of that atom. Okay? One last wrinkle in naming is what happens if it's wrapped in water. What happens if it's a hydrate? Okay, hydrates. So some molecules really, really like water. They're polar, and water is polar. So even when you dry them out, they grab water and hold on to it and like, no, water's my friend. I'm not going to let water go, right? And it's like a social clique. They have to hang out with water. And so even though it might look dry and crumbly or dry like a crystal, there's water in that molecule. It's wrapped in water molecules. We call those hydrates. And so the molecule inside that is like the central personality of the social clique, that molecule we name whatever it is. And then we have to tell people, but when you spoon that into your beaker, you're not just putting that central molecule in, it travels with water. There are water molecules wrapped around that. And so we call it a hydrate. And we're telling people it's not just that thing, it's that thing, and it comes with water. Well, how many water molecules are there that travel with the one thing that we've already named? What's the ratio of that thing to water molecules? So then we use Greek numerical prefixes to before the word hydrate to tell us how many. You could say anhydrate, which means there's no water there. So you could say anhydrate about everything that isn't a hydrate, right? So kind of silly to say anhydrate, but you could. No water. Or you could say monohydrate, and that means that for every one molecule of this thing that I just named, there is also one water molecule, and they travel together. Or you could say dihydrate, trihydrate, tetrahydrate, quintahydrate, hexahydrate, heptahydrate, octahydrate, whatever it is. And that's how many water molecules are traveling with every one thing that I just named. Okay? Let me show you a picture of that. So here, this is methane hydrate. And so this is a methane gas molecule, CH4 natural gas, the stuff that comes out of the ground from decomposing organic material, and we use it to cook our food, right? But it can freeze. You can freeze methane gas and crystallize it. And when you crystallize the methane gas, it likes to have water around it. It likes to take water friends. And so here's a molecule of methane, and here's a bunch of water molecules in a lattice work around the gas molecule. So you don't just have methane, you have methane nonahydrate or something like that. And it's traveling with, all these water molecules are traveling with this gas molecule. This stuff is cool. I tried to get some to show you, but it's very, very expensive and hard to transit and all that stuff. So instead I found a video. And what this looks like, because it is crystallized water, what's crystallized water? Ice. But it's ice wrapped around gas molecules. So can you light an ice cube on fire? Not a normal ice cube, but you can light these ice cubes on fire. Weirdest thing, blows your brain. So I just wanted to show that to you because it's fun. So here it is, being fun. Somebody's trying to be like Star Wars. Let me get to... They actually do it because.
Hydrate,
So
ethane hydrate, propane, number of different structures. So liquid nitrogen is very cold. It's about 100 degrees colder than the temperature at which these hydrate samples would dissociate when they would decompose to ice plus gas on the tabletop. And here we have a little piece of methane hydrate. It's enclosed in a soft metal jacket. The samples we make are polycrystalline. They look like snow. It's like compacted snow. But honestly, it does contain gas inside. A little piece off here, and as it warms up, you'll begin to see it pop. It's reverting to ice plus gas, and then as the ice would melt, as it continues to warm, it'll end up in water plus gas. So this will form anywhere you have water and gas at moderately low temperatures and high pressure.
So what's happening there is
My name is Steve Kirby.
the water is being blown apart as the gas becomes more volatile.
I work with Laura Stern, who's also a geophysicist in this lab that is devoted to the investigation of planetary
So
ice
there's hydrates that they naturally find in the
Gas
water
hydrates
or in the base of the ocean.
very remote places.
This is the part I want to show you.
This is a sample of, this is a structured tube gas hydrate. It's predominantly methane, there's a little bit of ethane in it. I'm going to demonstrate that by lighting the sample on fire.
So it's looks like snow. It's icy, crystalline stuff, but the snow burns. I think that's just awesome. Yeah, it looks like marshmallows, but it's not. It's ice
It's
crystals.
decomposing to ice plus gas.
That's strange.
The gas is flaming, and the liquid ice will soon just melt up water. You can see it's not just a pile of snow that I'm shoving it.
They contain abundant amounts of natural gas. This natural gas is thought to be a significant potential resource for our energy needs later in this century.
So there you go. That's good enough for now. So these are just cool things. That doesn't have much to do with naming, but as we were talking about hydrates, I thought I would show you something cool. Question? You sure? Oh, okay. Any questions? Yes. Okay, so there you go.